Right, section B in the AS papers is all about practical skills. And this one is analysis skills. You've got to draw the graph. So all those graphs that we draw by hand in lessons, they are all worthwhile because it's a skill you need to show in the exams as well. I know we've enjoyed using Desmos over the past few weeks during distance learning. However, the old 30 centimeter ruler and graph paper needs skills. Those skills need to be sharpened like your pencil. Anyway, right, here we go. So this is all about it's materials, it's fluids. It's all about density, and in particular something called Archimedes' principle, which states that the weight of the fluid that's displaced is exactly equal to the value of upthrust on the object that's floating. So, but anyway, it gives us this equation here, right? A student predicted that the relationship between the density of the liquid, rho L, and the depth of the block will be given by this equation here, where rho s is a constant. That's the density of the block we're using. So we're keeping the same block, but we're varying our independent variable. The thing we're changing here is the density of the liquid. Because if you have a look here, we've got 5 different liquids to play with: honeycomb syrup, seawater, vegetable oil, and baby oil. Sounds like a really messy practical. Anyway, there's the equation there. So just rearranging this, I'll just do this quickly just to show. It tells you, I mean, it's like I said, it's signposting which, the route through this question quite obviously. We're plotting rho L against 1 over D. So let's rearrange this fella. So we've got rho L equals rho S x times 1 over D. Now, the reason I've written it like that is because that's on the y-axis. We're plotting 1 over D on the x-axis, which means that is the gradient. Y equals mx plus c. Didn't have to take that much rearranging, but there we have it. So the gradient of our graph should be rho s times x, where x is the depth. The depth here, isn't it? Okay. Right. So the third column, the fourth column rather, that's for the values of 1 over D. We don't need to convert because it's already in standard units. Plotting those, I've not actually plotted those, I've just kind of sketched those onto in that position. But we then need a straight line of best fit, don't we? And it pretty much is a straight line through the origin-ish. Okay, so explain how the data supports the student's prediction, right? Well, we've assumed that is in the form y equals mx plus c. And so if we plot rho L against 1 over D, because these two fellows are constants, okay. Sorry, x is not the depth. Yeah, sorry, D, that's the depth there. What's x again? X is... That's the dimensions of the block, isn't it? Height x. Yeah, so that's the height. That's the overall height of the block, isn't it? Okay, right. So explain how it's true. But we've assumed that the equation is y equals mx plus c. So the theory goes that if you plot a straight line, plot the points, you get a straight line through the origin. Okay, straightforward. Right. The calculation. Taking the gradients, I think the gradient should be, you've obviously plotted this much more accurately than I have. I've just literally just plonked points onto the graph paper. But gradient, right, we've got the gradient is rho sx, isn't it? So the gradient m is rho s times x. Now, with x is 9 centimeters, we know what's the gradient? I think the gradient's 50, isn't it? So yeah, I think it goes up 1500 for 30 across. So the gradient is 1500 over 30. That equals rho s times. Now, standard units, so 9.0 times 10 to the minus 2. Okay? So that gives us a value of the solid. Rho s is equal to 556 kilograms per meter cubed. Now, looking at the table there, that is most likely to be chestnut, isn't it? Okay, so that block is made from a wood from the chestnut tree. Quite straightforward, that question, wasn't it? Anyway, hopefully you plotted your points much more accurately than I did. Right, see you later.